Can I tell you what the fears are?
Yeah, I'd do that. Because you talked about at night, and I couldn't, but that time frame.
Here's what we're nervous about. The college has placed really high criteria. Because typically if the class has 15 students, don't worry about it, the class is going to run. They're going to set the bar really high if we do this, really high. And that's fearful because if you're already on the waiting list of the other one, and you sign up for this one, that means you're off the waiting list, and if this one gets canceled, you're going to be really upset. Math 15 was no big deal.
The thing is, though, I talked to Professor Miley Barron. I talked to her, and she said she's going to limit. She's like, because you'll just say, "Come in, sit down, and read them out." But she said she's not going to do that. She's going to limit her class.
Yeah, a lot of professors don't do that.
Because she says it's a very demanding class, and grading it is very time consuming and demanding. And she says, I'm not going to take more than the limit.
Yeah, Math 32 and 33 are horrendous for grading. Very heavy workload for that. Okay, I just want to know. I didn't mean to waste your time with that.
If you're gonna teach it, I'm switching.
Why? Miley Barron is awesome.
I like
We
you.
don't know her.
I don't know her. I like you.
Yeah, we don't know her because for the past year she's been on sabbatical. She's been working on a project. But she's back next semester.
What project?
What is she like as a teacher?
You had to ask. Let me put it this way. I remember walking up to her once, and I told her that I complained about her to the college. That I demanded never to teach in a classroom next to hers. Because she's so loud. But you don't fall asleep. It's a good thing. It's a good thing. She's very excited.
Wait, what does that mean?
She's very excited and happy, moves around a lot. And talks loud.
Were you actually like upset about it, or were you?
No, I was being silly.
Oh, okay.
But I didn't tell her that. So she's very, you can't fall asleep in her course.
Okay, so it's a lot like yours, because you have the one math course in all of Sierra College that I haven't slept in. Like, not even once.
Really?
Yeah.
You sleep in all your
You
classes?
should have seen him last semester. You should have seen him last semester. He sat right in the front. He slept every day.
Voice that
Well,
Yeah,
Debbie's
Debbie
voice
talks.
and her personality put me to sleep. Very boring person.
Oh.
So, it's nothing against me, it's everything against her.
You guys ever hear of Dan Defoe?
Yes.
Dan Defoe.
He's awesome.
I had a student. I mean, I turn on the TV just to hear him
Yeah.
talk on his classes.
He should be on television.
I had a student who complained that she would always fall asleep in his class.
How can you fall asleep in
That was
Dan
my
Defoe's
point.
class?
Why? What's his? Does he have like a really good?
Oh yeah,
Oh, yeah,
the guy just gets up there and he just emotes and like he really gets into it. He teaches history.
I gotcha.
If you take history, take it with him. Yeah.
I had what's his face? Some night teacher for history, and I swear to God, he had the voice of a metronome. Like,
Oh no.
it was so bad.
How do you what
In other words, it like never changed at all. It was always the same, and it was so
is that? It's a
boring.
monotone.
Yeah. Yeah, he was very monotone. Yeah, in other words, he was very rhythmic.
Yeah, but I bet if you wrote the board the letter rho, he could probably write it as well. So there are plus
This is very true, very true. And it was a nice class, so he literally lectured for 3 hours straight. Like, nothing but lecture for 3 hours.
I think you.
The physics, I just look at physics, so it goes to 305, that's the one, that's the latest one. So it
Did
goes
you say 3:30?
3 out of 5.
No, okay.
Oh, I was thinking more towards 3:30. See, my problem is, after my 2 o'clock class, I can stay for a half hour, but I have to rush off and take a kid to school, take him home.
Yeah.
And it would take me maybe up to 3:30 to get back.
Okay.
That's like a lot of time.
That 32 class would be full if you signed up for the course. I mean, there's like 15 people already.
Well, I don't know. That's why I brought it up here. I want to know how many people would really be interested. Catherine, what you said about Nevada County, I didn't think of that.
What are you
This is
talking
a
about?
really good plus. Well, she pointed out that offering it just 2 days a week is good for her because she doesn't have to drive as much.
Yeah,
You're not from Nevada? Or Nevada County?
Well,
Oh,
the
wow, so
Nevada County campus is so small, we can't offer the upper level courses. So a lot of the students who live up there, they have to come down here at some point to finish up their degree at Sierra College.
That really sucks. Like,
Yes, it does.
It's like so far away.
I had somebody in my class, and
Yeah, because the Truckee campus has hardly anything going. It's so small. So you guys, today, I'm gonna cover, what do we have left? 1 today, 2, 3, 4, 5 class meetings.
And there's only
We have like 9 sections, right?
5 sections left.
For 5 class meetings?
I don't know if we can do that.
Let's do 2 per day. Can we do that?
Yeah, we have one pre-day.
That way we don't get overloaded on
We
the
get a-
last
We
week.
get a review day.
Yeah, because we need a review day.
We get one review day on the last Wednesday.
Okay.
No, I thought we have our finals Wednesday and Friday.
Is it?
You guys, it's up to you. Do you want to have the exam over 2 days or just 1 day?
2 days.
Yeah, 2 days.
Which way do you like it better? What do you
Well,
suggest?
even if it's longer, that means we can make more mistakes.
Yeah, but you guys, check this out. How about when I come to class on next Friday, I will discuss quickly 14.7 to 14.8, so that when we come back on Monday, I'm done. We just review.
Okay.
Does that sound good?
That's fine.
Sounds great.
We only have up to 14.8.
Yeah, this only goes to 14.
You know what I was thinking? I have never ever finished a book in a math course. This is the first time.
Really?
Yeah, this is the end of like all the calculus that you take out of this book, right?
Well, you know what, on that note, hold it. You guys gotta remember that what the author really wants to do is, what the author of any book, a textbook wants to do is,
Teach you?
no, they wanna make money.
Oh.
And so typically, like for a book in a math class, there'd be a lot of sections that wouldn't even cover the course, because they wanna cater to more institutions that do cover those other topics. That's why sometimes you don't finish a book.
You also have to talk about the test, number 3. The double interval problem.
Thank you. Before I get started today, you guys, can you take a peek? Do you guys have your exams with you? If you don't, can you just listen to my words and check this at home? On exam, is this exam 3, is it?
Oh, okay. I remember that question.
Exam 4, can you look at number 3?
Use double integrals to compute the volume
Use a
of
double
cylinder.
integral to compute the volume.
Yeah, that didn't make any sense.
What?
Of a cylinder. And you gave us z coordinates. Wouldn't you want to use cylindrical coordinates in order to find that? Not polar coordinates?
Oh, I agree completely. I was twisting your arm. I wanted to see you do it the hard way.
With polar coordinates?
Yeah.
Okay, well, that's what I did, but
Okay.
I don't really, it didn't make a lot of sense, but I hope I did it right.
I take it back. I don't think it's difficult. I think it's pretty straightforward.
Yeah.
You have to put a function in diagrams.
But you guys, I got an exam sitting in front of me. I marked somebody down for using a triple integral instead. And I told you it was okay. Is there anybody in this room who used a triple integral? Come on, I know there was. Did I mark it wrong for him? Oh, good. So I'm glad I wasn't consistent. You're the only one I nailed. I'm sorry. Did I correct it?
Thanks.
Did I correct
No,
it?
you said wait till now.
Yes, ma'am.
Because isn't a double integral and polar just a special, is a special
I know,
case of a
yes.
triple?
Yeah, that's why I should not be attacking him for using that.
Right.
I think they're synonymous.
On that note, is
Yes.
could we use spherical coordinates instead of rectangular coordinates for number 6?
Not if I asked for zero.
Okay.
I nailed you really hard. Probably not attributed.
You gave me 2 out of 12 because I used spherical. I forgot. Because I read like symmetrical integral that will allow. I didn't read rectangular coordinates.
Oh, Green Bay must have been ahead then.
Oh.
I gave you mine back in the, back in the box already.
It's still here.
Oh.
I started done with it. So you guys, can I change the name of the game? Oh. Yes, you're sorry. Eric. No. No, I don't think I picked it up. Okay. Sorry. So you guys, we've had the fundamental theorem of line integral. The glamorized version, really, or should I say, analogous to the fundamental theorem from calculus part 2. Here's another really useful theorem. It's got a name. I'll call it Green's theorem. Now, if the conditions are right, I've got some kind of curve that's positively oriented. And when I say positively oriented, I mean I'm rotating in the counterclockwise direction. Or shall I say, I'm rotating in such a way that my hand's being put out, my left hand, and it's going to be on the interior of this curve.
So when you say conditions are right, it means certain things have to be,
Yes, before I can apply the theorem. Here's one of them. It's oriented in this fashion. I sometimes say it's positively oriented when I rotate in the counterclockwise direction. The curve has to be smooth, meaning no abrupt changes in direction, no corner points, no cusps. It has to be connected, not broken into parts. It has to be continuous.
Isn't that what your formulas mean?
Well, no, continuous means just no breaks. Yes, smooth
like an
refers to
absolute
differential.
value function.
Correct.
Okay.
Good example. I think I've got to have a vector field that has continuous partial derivatives. And if that is the case, then Green's theorem says the following. If I've got a line integral looking like something like, how about an f, a function f in two variables, dx, plus, how about g as a function two variables, dy. I can evaluate this line integral by using a double integral. Yes?
It might sound kind of dumb, but what's with the circle through the integral?
Sorry, I didn't even think of that. You guys, it's a habit I have. If I'm going to evaluate a line integral over a curve that actually is a closed curve, I have a tendency to put that little dot in there. You don't have to. This is what I just said. It means a curve C is closed, so it completely goes around. It's not a curve that does this in the xy coordinate plane. And I think I could evaluate this line integral just by using this double integral over my region D. And the double integral ends up looking at the partial of g with respect to x minus the partial of f with respect to y. Well, at least this is one version of it. This version I sometimes classify as circulation form. And where the f and g come from is that I've got to have a vector field that has as its components my scalar functions little f and little g. Now there is another version of this theorem that basically looks like this. To evaluate this line integral of, how about this time, my g of xy. Actually, guys, I think I misspoke. I'm sorry, I want to write it differently. I meant to say my function f. Egads. You guys, I don't know. Remember how he writes that second version of this theorem? I think the second version, which I rarely use, looks like this. Is equal to the evaluation of this double integral, the partial of f with respect to x, plus the partial of g with respect to y, and I'm going to be integrating over the area. So you guys, I'm nervous. I want to make sure I've got the order right on the second version of Green's theorem. So I've got the partial of f with respect to y, minus g with respect to x. You guys, I got it right. I just got a sign change error in here. A negative sign here, positive here. Now, don't take this the wrong way. If you're going to evaluate a line integral, these two are absolutely equivalent. The only real difference with these two is if you take a peek at the double integral, what's inside looks different because of my vector field that I refer to as big F. Now, the bottom version is what I sometimes refer to as my flux form for Green's theorem, and it's got these names for this reason. My vector field has this quality. Oh, I've got a point here where all the vectors are actually going in this direction, away from it. Then I can talk about the amount of work being done to leave that point. I can even talk about the amount of work done to actually come into that point. I sometimes refer to such a point as a source point, or over here I might refer to it as a sink point. For obvious reasons, if you think of fluid flow, I got a sink there. If I got a hose spouting out water in all directions, that's going to be a source of water. Sometimes I refer to the circulation form as a circulation form for this reason. That vector field really quantifies about, say, a certain point, the fluid flow I have in the counterclockwise direction. So, if this particular line integral evaluates to a positive quantity, it just means I got fluid flow in a counterclockwise direction. And if this evaluates to a quantity that's negative, it just means I've got fluid flow in the opposite direction, circulating around my various points in my region D. Here, it just simply means I've got fluid flow going out or going in, or if this is equal to 0, it just simply means the net flow going in and out is going to be 0. It's going to be the same. So, everybody, let's talk about actually using these versions of Green's theorem. And you guys, I don't have that many examples I need to give you. So hopefully that will leave me a little bit of time in the class to maybe prove partially this theorem. So first example, I don't remember what it is. I need to look. How about taking a peek at the evaluation of this line integral? So 5xy dx plus x cubed dy, where my curve C is described by these two equations. So pictorially speaking, here's my x-axis, here's my y-axis. I've got a part of a parabola and part of a line. So I'll refer to this C1 and this is C2. And I'm going to assume positive orientation. I just maintain to evaluate this line integral. What I really could do is just simply rewrite it. According to Green's theorem, let me use the circulation form. It's the form I'm used to. I'm going to rewrite this as my double integral over region D, taking a peek at the partial of my g function with respect to x. And then I'm going to subtract from this my partial with respect to y of my f function, which in this case is 5xy. And I'm going to integrate with respect to area. So in using Green's theorem, the key is I'm going from looking at a curve surrounding a region to the region D itself. And if I'm going to rewrite this as a double integral over the region D, let's quantify what the boundaries are.
What if the equations are indicating the arrow?
You know, I'm always going to assume positive orientation, which means with this curve that circles around itself, I'm always going to rotate the counterclockwise. Okay, if I don't, it changes sign. We just need to be consistent. To be honest with you guys, that's the only reason why I'm doing this. So you and I get the same boundary. So I think I can dive in and differentiate. Does that give me the double integral of, is that a 3x squared minus 5y? Ooh, excuse me, I misspoke. I meant minus 5x. So let's you and I integrate with respect to y first, then with respect to x. And if I do, that simply means my values of integration for y are going to range from
2x to...
Is it really?
Oh, x squared to 2x.
Yeah, I agree.
I don't know why I was thinking 2x.
What about the corresponding bounds for x?
0 to 2, right?
I don't know, is it 0 to 2? I'm sorry, I'm so slow. Yeah, I agree. So I think this point of intersection right here is going to be 2, 2? Actually, 2, 4. So I will be integrating respect to x from 0 to 2. Oh, you guys, maybe this is a bad example. That's a piece of cake to anti-differentiate, isn't it? So I guess this gives me the integral from 0 to 2 of my x cubed minus my 5 halves x squared, and I'm going to evaluate from, ooh, did I make a mistake? Yeah, I think I made a huge mistake. I just anti-differentiate respect to x.
Yeah, you got to do it with y.
So with respect to y, I think I'm simply left with this. From here to here.
That's gonna be a.
Is it really?
Well, yeah, you got like 6x cubed minus 10x squared minus 3x to the 4th.
So that's going to give me in this case,
Plus 5x cubed. So you have
so 6x cubed, you said?
yeah. So you have negative 3x to the 4th minus 10x squared minus x cubed, right?
Well, hold on, I still haven't finished. So is that a minus?
Oh no, I take that back.
3x to the fourth. My goodness.
Yeah, minus 2x to the fourth.
Wait, no, for the next,
I'm on the wrong one, I'm doing the x squared first, I'm sorry. I meant to say, is that gonna be a 6x cubed?
Yeah.
When I corrected it, I was looking downstairs. Is that gonna be a minus 10x squared?
Yeah.
Okay, I lost track where I'm at. Is that gonna be a minus
Minus
3x to the fourth, and then a plus
5x cubed.
5x cubed, I got it. I agree. And I'm integrating back to x. I suppose I can combine a couple of terms. That's 0 to 2. Is that a negative 3x to the fourth? Plus, is that 11x cubed minus 10x squared? And anti-differentiating, it gives me a negative 3/5 x to the fifth. Plus 11 quarters x to the fourth minus 10 thirds x cubed. And I'm going to value from 0 to 2. But that's simply going to give me, is that a negative 96 fifths? Is that an 11 times 16 over 4? Is that a minus 80 fifths? I think that's going to be a negative 96 fifths. Plus, is that 176? Or more?
Why not? It's just 44. Oh, yeah, but you want to
Ooh, nice, thank you.
do fractions or what?
wait.
So can I just rewrite it? Yikes, 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 you guys, what does that give me?
Ugly.
So I got a single fraction over 15. Is that gonna give me a negative?
288, I think. At 400.
So minus 400.
Yeah, and then whatever 44 times 50. So what is that, 600, 690?
690. I trust you in that one, I couldn't do it in my head.
Well, 40 times 15 is going to be 600.
Yeah, you're right.
Plus, no, 660, not 690. 44 times 15, 660.
660, okay, gotcha.
For some reason I was thinking 46 times 16.
So you guys, what does that give me in the end? Is that a negative 28? Negative 28 15ths? Does that make sense? Yeah, it does. Because if I got this vector field described by this beast right here, my vector field f bar really is nothing more than this. Its first component is 5x1. Its second component is just simply x cubed. And I just maintain through that vector field, the amount of circulation I have going around the curve is going to be in the overall in the clockwise direction. It's going to be positive, negative circulation.
Okay.
You guys, did I just give you a problem that I could have done directly?
Say that one more time.
Could we have a guy design integral directly? Yeah, I could. Do you guys think I can take a few minutes off the clock? Can we just see if I'm correct and actually answer the question completely differently? So,
Before we do those,
yes,
isn't it supposed to be a smooth curve?
it's supposed to be a,
It's supposed to be a smooth curve with no cusps.
Oh, yeah.
that's true, but when it comes to smoothness, what really I need is I need it to be smooth and continuous over most of the points. In other words, I can. No, this is important. When I say most, I mean I can be non-smooth at a finite number of points. So, as opposed to infinite number of points.
Okay, so our definition of smooth is now tweaked.
Yeah, because for the overall curve, collectively speaking, I could be non-smooth at a finite number of points.
So what would a curve
basically, it just has to be smooth in the area you're integrating over? Is that what you're trying to say?
Yeah, well, no, because I can break it up into smaller pictures. Even if I had a corner point right in the middle,
Yeah.
I can break it into two different intervals.
Well, yeah, but then,
Then you
then
can
if you're breaking it
integrate
into two different intervals, then you're making it smooth in the area. that
Yes,
you're
okay,
integrating
I'll buy
over.
that, I'll buy that. As long as you break it into smaller
So can you
parts.
draw an example of that wouldn't work with Green's theorem because of the non-smoothness?
So infinite.
Infinite break.
One of those.
You guys, I need to write
called
it.
absolute value function.
Yeah, I will, but I just wanna break some work.
Wouldn't an absolute value function be one of those things?
Yeah,
that
that'd be a
brings
perfect
standards
example. Here's a nice one. Well, Catherine, this may not answer your question yet, but give me one. What about this function? In other words, let the output of this function be m over n if x is rational. And if it's irrational, it'll be n.
What? Come on, you can't tell what all those symbols mean?
I think that function
Yeah.
is non-continuous at infinitely many different values of x.
So what's this double barred z supposed to mean? Really?
I'm using the letter z, uppercase z, to stand for the set of integers. Oh, I can't. You might confuse it with a variable, so I'll boldface it. I can't do that in textbook. I'm at the ink board. So I typically put a diagonal line, just so you understand it's the specific set, the set of integers.
Okay.
Okay, good luck.
Well, if you in an area, a bound,
Yes.
isn't that, couldn't you, no, never mind.
I think this is a beautiful example of a function that's discontinuous at infinitely many values of x. It doesn't really answer your question, though, Catherine. How about this one? This is a common function. Let's consider one that has a quality. That is what an engineer might call a sawtooth wave. But next, let's continue to build this function by, with each of these line segments, looking at their midpoints and connecting. And then continue to repeat that process over and over again. That'll give you a nice example that's non-smooth at infinitely many points. And so that's when I really do this.
So it's all approaching zero?
Yeah, it's a pretty sophisticated example. Notice how I just drew a picture. I don't write it closely.
As part of the reason we still use Green's theorem on that is because, for our purposes, the functions are still continuous between the intersection points.
Okay, I like the way you said it. I agree. So that's what I said, mostly smooth. So you guys, check this out. Let's see if we can get some practice. And evaluate this line integral using a different technique. I didn't know what the answer was. But let's just make sure we get the same answer. I'm sorry, am I putting you to sleep?
Yep.
Sorry. So you guys, check out curve 1. I think this is equal to line integral over C1. Where with C1, I've got the equation. You guys help me with this. Was it y equals the x squared? So I think another name for this y is just simply x squared. I think another name for this dy is going to be 2x dx. And therefore, in the end, I'm going to have the integral of 5x cubed plus 2x to the fourth with respect to x, and I'm going to be integrating from 0 to 1. That being the case, doesn't it clearly evaluate to, let's see, is that 5/4 x to the fourth plus 2/5 x to the fifth from 0 to 2? Or shall I say, that's simply going to give me, is that a 20 plus 64/5? You guys have a case so far?
I have a question about
Yes.
that. So, like in this example, we saw that circulation was going against the way we had the curve oriented. So with this integral, what does the positive result mean?
It means at least along the curve, the fluid flow with the vector field is mostly in the opposite direction. Yes? this error?
So, you just chose one of the lines to use.
One of the curves, yes.
Yeah, that's it. Yeah, you just chose one to use arbitrarily when you took the, okay, I did.
Oh, you guys, let's check out C2. So over C2, I guess what's in the integrand's position is going to be different. Hold on, I said C2. So in the integrand's position, what do I have? Is that going to be a 5? Well, if this curve's a linear one, y equals 2x, wouldn't that give me a 10? X squared dx? However, with my second term, my dy is simply going to be a 2. So is that going to give me a 2x cubed? Or shall we say, we've got the integral from still 0 to 2 of my 10x squared plus 2x cubed with respect to x. Yeah, I think I'm 100% wrong. Because of the flow of the curve, I think I'm actually starting with an initial value of x that's actually 2. And ending or terminating a value of x which is 0. So let's evaluate. Does this give me the following? Do you guys think I can just convert it to subtraction? I can anti-differentiate to get this. But since I changed my sign, I will go ahead and reorient my order of integration. Well, at least the order of evaluation of the same thing. And I think at the end, what I'm going to be subtracting is nothing more than a, jeepers, is that an 83rds? Minus an 8? Or shall I say, that's going to give me a positive 12 plus a fraction, whose denominator is 15. Whose numerator is going to be 192 minus 400. Or shall I say, that's going to give me my 12 plus my, is it a negative 208 or 15? But that's going to be something minus 208 over 15.
Is it 190? 144 plus 36?
Well, it's going to be a 150 plus 30, 180.
Yeah, I was off that.
But that's going to give you a negative 28 over 15. Oh, you guys, thank goodness. I didn't commit any arithmetic errors.
Wait, why do you have 10x squared? Where'd that come from?
So, Matthew, that came from taking this as my y. So replacing this y with my 2x.
Okay.
Because it's parameterized in terms of x. Matt?
And then you subtracted C1 from C2?
You know, I didn't. I was actually adding them together. So I was adding these two particular line integrals.
You always do that?
Just because we're going off.
Maddie, I probably was just wasting our time. I could have kept a pause. I was just saying in my head, well, let's change these two.
Oh.
But when I interchange the variables, the balance of integration, I also got to change the sign of the evaluation of the variable. And where that comes from, really, back in math 30, it came from the fact that dx was the limit of a Riemann sum. That I said dx. I meant the delta x is b minus a over 2. So when I swap them, the a minus b becomes negative, but the b minus a. You guys, before I get rid of this, so far so good. And
Hey, Brad, I had a question about
Yes.
your example that you erased of the where it's not smooth.
oh, so the waves,
Yes.
the sawtooth wave.
Well, no, the set that you wrote down. For the
Gotcha.
second part where you said that you had 1 over x, you said that there, if there exists an m and an n such that x is m over n. Do you mean m and m are still elements of the instances? Or?
Oh yeah, I even had that on there. I said,
Well, for the first part, how about the second part?
oh, and if I didn't write it, that's what I meant. I'm saying, I simply meant, if x has a quality that does not exist in m and n from the set of integers, for which it could be expressed as a ratio.
Oh, you missed the not. You didn't have a not in there.
Yeah, I
reading
might
the
have just
not.
said it out loud in English. In other words, to say it more succinctly, if x is irrational, use that example. If x is rational, just use the sign. So you guys, how about something like this? How about evaluating this line? I've got my 2x y dx plus my x squared plus y squared dy with my c being this hyperbola, or excuse me, ellipse. So you guys, using Green's theorem, rewriting this as a double integral. I think on the interior, I'm just going to have the partial of my second function, my g with respect to x. But that's simply going to be a 2x minus the partial of my f with respect to y, which is,
We're still writing down.
I heard that. Now you guys, let's find the bounds of integration. So do you want to use polar coordinates or rectangular coordinates?
Polar,
Which one?
polar,
Which one?
who cares?
The answer is who cares? Because look at the interior, it's already zero, isn't it? So I think for free, no matter how I quantify or however I describe that region D, I think the evaluation is zero.
What does that mean?
Oh, I'll talk about that.
I'm just gonna ask if does the vector field have to be conservative?
No, that was a good point. So you guys check this out. What this really says is that if your vector field is conservative, look at this vector field, F bar. Isn't it just simply this?
Does zero mean the vector field is conservative?
Well, yeah, but I want to justify it. I want to just say it. So check this out. If this vector field is conservative, doesn't it mean the partial of f with respect to y and the partial of g with respect to x are equal to each other? Oh, but wait, hold it. That means if these two are equal to each other, that's always going to be zero. So I think for a closed curve, as long as the vector field is conservative, that line integral will always evaluate to zero. Now, I didn't have to use Green's theorem to show you that, technically speaking. What did we talk about last time? To evaluate an integral over a vector field, this was nothing more than my potential function f eval at r bar b minus my scalar function, which was my potential function f eval at r bar of a. But you guys check this out. If this r bar describing my curve C is a closed curve, and it doesn't matter what point I'm looking at, these two values are going to be the same. And so I even think with the fundamental theorem for line integral, that vector field is conservative and I'm integrating over a closed curve C, this has to be equal to zero. I've proven to you in two different ways why these line integrals have to value to zero if I've got a conservative vector field and the curve C is closed.
Can you say what you said about when you were doing that top thing up there with the partials equal? Is that if the partials are equal then?
True, but these partials are equal to each other as long as the vector field is conservative.
Oh, yeah, oh.
By the way, what does conservative mean? What does it mean to say a vector field is conservative?
No work done.
No network done.
No network done.
What is that?
That's a result.
Okay, there's no.
That's a result.
Work. So,
But what's our definition of a conservative vector field?
Means you can find that.
It means you can find a potential function for which the gradient vector is equal to it. Good.
that is so fancy. No
Wait.
network done.
But when you talk about no net work done, I mean, I think that's a result of having a conservative vector